you have already the proper assessments. Is there anything that says black screen? Well,
What do you want to do?
now let's not touch it, Martin, because we'll waste time. Let's not touch it. Let's move.
What are you trying to do?
No, I was trying to see if I can pull a little bit more light there, but eventually I can't. Okay, so what is testing for proportions? When you test for means, you have a quantitative variable. When you test for a proportion, you have a Bernoulli random variable, which is what? It's a categorical variable, okay? So X is a Bernoulli random variable, and in particular a categorical random variable. And what we want to find, what we want to test for the probability of success, which is the probability that X takes the value 1. So this is our test about. And the hypothesis would be the following. Alternative, actually the null is always P equal to a set value, which I call by P naught. And I can have the following alternative hypothesis. Either P is greater than P naught, P greater than less than P naught, and P different than P naught. This is, what kind of test should we do here? This is a left tail, this is a right tail, and this is a two-tail test. Now, in the process of doing this, I want also to introduce another concept, which is the so-called p-value. I want you to learn the p-value very well. First of all, do we understand why I have right tail, left tail here, and two-tail test here? I guess the two-tail is self-explanatory, quite self-explanatory. Why do I have a left tail here, a left tail test, and what does the left tail mean? No, the critical region is on the left of the bell curve. Okay? Here the critical region is on the right of the bell curve. That's what it means, right and left. Now, what is the test statistic that we use? Okay, the test statistic comes essentially from the approximation of the binomial distribution with the normal distribution. So the test statistic is exactly what we called before p hat, and is the sample proportion. And it's nothing else but the sample average, x bar, where you have, if you have this one, x1, x2, x sub n, what values are these taking? These random variables are taking. What kind of values are they taking? They all take the value 0 and 1. So depending on the response you have, you get 0 and 1. So forth and so on, okay? And they are independent. So this is random sum or identically distributed. So when you calculate x bar, then of course you add the ones and you divide them by n. So that's why you have the particular instance, x bar is equal to the sample proportion, the number of those variables who turned in the value 1 among the sample of n. That's called the sample proportion. You went out and you asked 20 people about their opinion, and 10 said yes, and the other 10 said no. Well, the sample proportion is equal to 50%. That's what I mean. The sample proportion is not exactly the value of P. That's what we're testing for. We're testing to we use the input, which is the p hat, and we're testing an assumption about p. Now, what do we need to have? We must have a random sample of n greater than 30 if essentially p sub 0 is between 0.3 and 0.7. I mean, the closer to 0.5, the better things become. Now, if p sub 0 is closer to 0.5, then a sample greater than 16 will work as well. What will not work is if p is very small, becomes less than 0.1, then you need a big sample.
Or just use Poisson.
Or you have to use the Poisson distribution. Okay? But then the test, you have to invent the test if you use the Poisson distribution. And the Poisson distribution is discrete, so it makes your life more difficult. Since the test I will develop is only for the normal distribution, you really need a big sample. In these cases, the samples have to be greater than 60, even greater than 100. The smaller p sub 0 is, the bigger n must be. Okay, so the smaller, there is no way that this will not work. It will work. The problem is the size of the n. That's where the problem is. The smaller n sub 0 is, the p sub 0 is, the bigger n should be. Okay? And don't forget that in all cases, so that's one general assumption for the sample size. The second assumption we need is that n times p sub 0 and n times 1 minus p sub 0, p sub 0 is given to you. It comes from the null hypothesis. So essentially you have it. It's not something you have to guess. You have it. Should be greater than or equal than 10. Those are safe assumptions. So let's recap the assumptions we need. We need a random sample, and if you have suspicions that the sample is not random, is not very good, then you have to mention it. If I gave you one problem today in the homework where you had I think I did it. I solved it with the 6 samples where one was way off. That was a sample that probably that you are in a case where you may not have a random sample because not all numbers come, not all observations come from the same distribution. There might have been one station that was giving something meaningful, and that station, of course, in that station the conditions were not prevailing, so the concentration, the lead concentration was not the same as in the other stations, meaning that the mean was different, so you didn't have the same distribution. That would violate the assumption of the random sample. So in this case, the statistics don't work, essentially. Well, you work the problem, I worked the problem, but I kept that in mind. And accordingly, I phrased the final result. Or I did a little bit of additional study under different scenario. That's something that you always need to be careful. So we have those, all right? Those are the assumptions. So what is the test statistic now? What is the test? We take Z, that's our test statistic. And what is the distribution of Z? Yes, standard normal distribution. The test statistic And Z here is P hat minus P sub 0 divided by P hat times 1 minus P hat, P sub 0, excuse me, divided by the N, all this square root. Okay? That's it. Oh, by the way, I don't know if you like this, but you will find it very helpful. I took it from one of my other books, but I think it's very, very nice to have. I'll Xerox it, and also has tables and also has some other material that you may find quite useful. And then what do? I compare the value of my test statistic with the critical value. Or I find the so-called p-value. So what is the p-value? Let's say p-value for the right tail test. The p-value for your right tail, the p-value is always the type 1 error. So it's the probability, it's a type 1 error probability. So what is the condition when we do the type 1 error?
So you have the condition, you don't.
What is the condition? It's a conditional probability. So what is the condition for a type 1 error? What? Null hypothesis true, that's the condition. Okay? So when I say null hypothesis true, in this particular case would be P equal P sub 0. True. And what is the type 1 error? You reject the null hypothesis. When do you reject the null hypothesis for a right tail test? If the value of your test statistic is on the right, okay, of your significance level. So here, for the p-value, what you use is values of z greater than or equal than the value of your z statistic. And I would denote that by p hat. So that would be. So essentially, this is the rejection, it's the probability where the rejection rule is not phrased based on the critical value, which you have from the significance level, but is being replaced by the value of your test statistic. And graphically, this thing would appear to be the following. If we accept with the approximation of the, we're in the standard normal regime. So here is 0. That's the bell of the standard normal. The bell curve of the standard normal, not a bell. The bell is a bell. And the value, when you plug into the formula p hat, so that is what I call here in this z of p hat, because it's a value that depends on p hat. So if that value comes here, the area that represents of whom, the region of whom the area is equal to the p-value is actually the yellow area that I'm showing here. So that's the p-value for the test. Now, for the left tail test, you will have the symmetric. Yes?
Does the definition of p-value also apply to the hypothesis test, or is it specifically to...
No, it applies to all tests. I simply didn't have, this is a statement that applies to all tests. Whenever you do hypothesis testing, you can have the p-value, because it's a probability of a type 1 error. Where the type 1 error now is replaced is this exactly, is this thing. Why do I call it type 1 error? Because it it's an error where I reject the null hypothesis, although the null hypothesis is true. Actually, not although, given that the null hypothesis is true. This thing is even darker, correct?
That's the same.
Is it okay?
So, so what is the value that we are comparing, and how do we get it? I mean,
What is the value? You will see examples where we take the p-value. Okay. Well, let me just do some examples here. I found a very nice, kind of an interesting study here, which says, are pilots of risk due to fatigue? And it's an article that Journal of Safety Research. I like this kind of research. It's easy to do. I mean, the statistical analysis is just a joke in this paper. So what the problem is, look at the problem statement. That's very important. Let's look at the abstract. There was a concern, and actually this concern flared here in the U.S. after the Buffalo, the Buffalo, New York accident where the Continental Express went down quite late at night, about 10:40 in the night. And essentially that accident was an accident that could have completely been avoided. Of course, there were some confounding factors that once the pilots did their initial errors, those confounding factors became very, very dominant, and the plane lost buoyancy, and actually it ended up concentrated, crashing in an area where the debris was extremely small. It actually fit in less than half of the backyard of a house, and didn't destroy all of the house, so you can understand how small it was. The plane went just like that down. Now the incident started, actually the chain of events started once the pilots forgot to monitor what was their airspeed. And both were fatigued. They had many hours, that was their last leg of flight that they were flying, they were landing, and after that they would go to their hotel to rest. But the problem was that the previous night they didn't get enough rest, especially the co-pilot had to sleep on an armchair. So she was inexperienced. On top of her inexperience, she was also very fatigued. So what they did is that they didn't pay attention to the reducing, to the airspeed that was being reduced very rapidly. Now, if basically if the weather wasn't bad, there were no icing conditions, and they didn't have a light wind, they could have avoided the accident. Had it been a sunny day, that accident could have been avoided because they had poor visibility, they had all of other factors that essentially they shouldn't cause an accident, but given that their monitoring was very poor, the monitoring of their flight conditions was very poor, it led to the accident. Of course, it was unacceptable for pilots not to monitor their airspeed once, especially since they were on the approach phase. That's something that you should always monitor, and you should always check with first officer to see if you have, if there are any discrepancies. Because if there are discrepancies, then you have to avoid troubleshooting the discrepancies, and that's a difficult situation. It requires quite a bit of expertise.
So, I'm guessing that this study is not studying the amount of fatigue.
No, this study is trying to say, is trying to raise the following, trying to prove the following. Let's see the problem. Who wants to read the problem? To give me a little bit of break.
Into months.
Hmm?
We can't submit to months. Unless, then if
Common
we
concern in
schedule,
aviation
and
community
yes,
that pilot
specified
schedules
procedure.
can lead to fatigue. That wasn't the only one. There was another one that was
What I'm
due to
saying is
pilot
we can't see it
fatigue.
all.
In a morning flight, 2 pilots went into the wrong runway, and they had a heavy plane, and they crashed because they didn't have enough airspeed. And they never realized, neither them nor the flight, nor the control tower, that they took the wrong runway. They shouldn't have taken this runway. Now, that also revealed another problem. That particular accident revealed another problem, that the plane was also quite a bit loaded, because the people's average weights, according to FAA, are 175 pounds. Now, who of us is less than 185 pounds is probably something that would be very funny among us, the men. Now, females, yeah, most of the females would be less than 175 pounds, but in case where you have a tight flight and a short runway, weight can play a big role. That's why now for small commuter flights, they get the actual weight. So you step on a scale and they get your weight, and then they have the proper weight, the total weight. So that was another fatigue accident. So the concern is the following, and especially as you will see, the method of the analysis here, the hypothesis here, all right? There is a concern in the aviation community that pilot schedules can lead to fatigue and increased chance of an accident. That's what it says here, an accident. Yet, despite this concern, there is little empirical analysis showing the relationship between pilot schedules and commercial aviation related accidents and pilot work patterns. So this is what the study wants to identify. So the study says here, the study attempts to demonstrate the relationship between pilot schedules and aviation accidents. So the question, the hypothesis that is testing, are aviation accidents and pilot schedules correlated or not? Is there one influencing the other? This is exactly what sometimes we call explanatory variable. So is pilot schedule an explanatory variable for aviation accidents? That's what the study is asking to find. When we say one variable is explanatory, essentially you pose some causality. Now the problem, what we'll do, what the study will do is that the study will find whether there is a relationship, whether this random variable, pilot schedules, which it will measure fatigue as a random variable, and aviation accidents are independent random variables or not. And there is a test for independence what's called the chi-square test. Now, of course, the problem is that we will not do this particular test today, neither we will teach it in this course. We use the contingency tables. We don't really have time to do that. We're short of a couple of weeks in this course. We need 1.5 more weeks to make the course complete at that level. But now you will see some hypothesis testing that I can derive. So let's go to there is a blah, blah, blah here. So it says captain duty hours and accidents by length of duty. So those are data that were collected by major airlines, major commercial airlines, which are certified to carry passengers in the United States. And of course, here you have on your left column, you have hour in duty period. Then you have captain's hours. Captain's hours is experience. And then you have a quantity which is called exposure proportion. Now, why do we have this exposure proportion and accident proportion? Now, what is called an accident, and sometimes there are several things that are called accidents that passengers don't even feel them. There may be, there are 90% of the events that will occur and can be considered as accidents in a cockpit will never reach the passenger's attention. Will only be logged in the flight recorder, the flight data. The pilots will resolve them, will troubleshoot them, and you probably will never notice. Okay, for example, a tire breaks during landing. That's an accident. That's an accident. They don't have to be fatal or lead to an emergency, a serious emergency, or to any injuries to be called an accident. But there is a clear rule. So what we call here accident proportion is actually quite accurate measurement. Now, exposure proportion is a quantity that essentially during the time of the study, the officer, the one who collected the data, who is actually this good is from the Federal Aviation Administration, reasoned the following way: the more you fly, the more likelihood for an accident you have. It should increase. Okay, actually, the longer you fly, the more likely it becomes that you will be involved in an accident, because it's natural exposure. Yes.
Well, I'm just looking at this data, and I'm wondering which one of these is time, because I noticed hours in duty.
Hour in duty period. Now, you start your day, you may have a 12-hour day. However, you don't fly all of those 12 hours. Some of these hours you are a passenger, some other hours you are in the resting area. And for long flights that are over 6 hours, major airlines have resting areas for the crew, where they can go and rest flat. Actually, the newer jets, right where they have the compartment which is pressurized, and that's where we put also the dogs. They have a module which is like a huge luggage module, which has beds, flat beds, where you can switch off the light, because if you don't turn off the light and you don't lie flat, then the resting is not as good. And of course, if you have not rested under stress, you are more likely to make mistakes, fatal mistakes. So hour in duty period means the guy starts from the moment they check in till the moment they check out. So 1 to 3 hours. And you see most of those pilots pretty much, if you see the exposure, the accident proportion. Now, accident proportion relative to exposure is the quantity that you really want to measure.
Why? What is that?
Because it's a way to normalize. Look, pilots who had 13 or more hours, for those who have only 12,000 hours of error, of flying time, of records. So the cumulative record for all of these people is 12,000 hours in our data. For 1 to 3 hour duty, we have 430,000 log hours.
So
How can I assess data that do not come from equal lengths of observation time? So essentially, your captain's hours are observation time for this. So I need to equalize the observation time. For this, they have the accident exposure, which you find if you normalize, if you see the number of accidents that you have, and you divide them by the captain's hours. That's the proportion. That's what it calls proportion. And then that's the exposure proportion. The accident proportion is essentially the 15 divided by 430,000 hours. And the normalization is in the random variable that I'm interested in is the very right column, which says accident proportion relative to exposure proportion. Okay? And so those are proportions. No, actually, those are continuous random variables. It's a continuous random variable. I can take it as a proportion because look what I have here. 13 or more, 5.62. So the longer flights, look this gradient here. Between 7 and 9 hours, 1.65. When you go to 12 or more, yeah, let me get into my, because I can't see it from close up. I don't have the overview from close up. Yeah, for 13 or more, you have 5.62. For 10 to 12, you have 1.65. The accident, the numbers change a lot, we would say, dramatically. Yes?
How do you get it to 1 on the last one? Are we supposed to sum 0.79, 0.84?
Because we have hours including period, measured in pattern hours.
Okay, so we have this question. Let me just go back.
Number. So, yeah.
So we have this question. Is the rate of airline accidents smaller? When I say the rate, what do I ask for? What is the question? It's proportion, okay? So I'm trying to estimate the proportion. I'm trying to talk about the proportion, make an assessment about proportions. That's what I mean, rate of airline accidents. Smaller for long flights than for flights between 1 to 3 hours. You want to read the study a little bit so it can help us find what the sample size is? Data. You go here where they say it will be methods. Method. So there is a clear definition, as you see here. About accidents. Accidents were recorded from 1978 through 1999. And what did they call as accidents? Significant or substantial damage to the aircraft, at least. So that's what they called as accident. Or turbulence-related accidents were excluded because those can involve significant damage, especially during landing or takeoff. And so they got 55 accidents that they recorded, and therefore, let's see now how many pilots participated in the study. How many pilots were recorded? Well, we don't have that. So what are we going to do?
Captain's hours.
What?
The chance that during their hour dating period.
What is the right thing for proportion here, since we want to estimate proportion
Captain's
or
hours.
rate?
Captain's hours.
Does it remind you of anything else?
So Poisson distribution.
Why Poisson? Why is the Poisson?
As the time increases, we are measuring the chance of failure.
So what is this accident proportion that says here? We have 15 accidents. Let's see, what is this 15 accident? What is this 0.27? Where does this 0.27 come from?
We have more measures from 1 to 3 than we do for 13 or more.
15 over 55, correct? So you have 55 samples, So 55 samples give you an accident of proportion 0.27. Correct. So what should be the sample? 55. So if we want, we have a sample size of 55. Okay?
But isn't that not,
Wouldn't
That's a
the
good
sample
question.
size be captain hours?
No. If you try to go by captain hours, then you will end up with something else. Estimation of the mean of a Poisson. Because you involve rate of a Poisson there. It's hours. Your rate of accident per hours. That's the difference. So the sample size is 55. And now I'm asking, is this random or not?
No,
Can I take it as a random sample?
no.
Why not?
Because in order for a person to fly 13 or more hours, they must have successfully flew 1 to 3 hours, 4 to 6 hours, 7 to 9 hours, and 10 to 12 hours. So they would have a 3
No,
hours,
nobody flies
9
more
hours.
than nobody flies more than 13 hours straight.
55 represents the number of accidents.
55 represents the number of accidents.
So if we look at 55, we're only looking at flights that have accidents. So we're still looking for observations in which an event that we're trying to monitor that really occurred.
Okay, so, but those are all the accidents between 78 and 1999. So it's a census.
Yeah. But you're more likely to fly in less
So
hours.
why not use that?
You're more likely to fly in less hours. And as I was just saying, in order to fly 13 or more hours, you'd have to already have flown 1 to 12 hours. Which means that you would have measurements in all these things, which means
So
you would, in order
when you have census, then you know the distribution. You no longer have, of course, a random variable because you have recorded everything. There's nothing random anymore.
That's true, yeah.
All are facts. Everything is on the table. Cards open. There's no randomness anymore. The randomness involves the future. All these are full, complete observations. Okay? And therefore, in this case, when you have census, you cannot deny that this is the right result. This expresses what is the tendency, at least at a given time where the study has been recorded.
Well, yeah, but
That
in
should
this
be the
case-
tendency for the future as well. Correct?
Yeah, but in this case, the tendency is.
What is the random sample?
If you have in this case.
What is the random sample? The
if you have
random
an
sample is the
accident, it will be 1
smaller.
to 3 hours.
Mark, the random sample is when you take a subset of the population. Here we monitored all the data. We did census. We conducted a census. We no longer have a random sample. We have the entire population. There is nothing random about our sample. We sampled, we have everything. The entire population is in the sample. So, indeed, that 0.27 is the accurate proportion. You don't have to do any estimation, any confidence interval estimation here to estimate that 27 is the proportion.
Yeah. It does
And
not represent the probability. but
0.5 and 0.05 is the proportion for the accidents that happen, the probability of an accident happening on a longer flight, where the pilot is on the 13th hour of the duty. Now, beyond the 10th hour, pilots between the 10th and the 12th, basically they are about the end of their duty. I think if you are the new rules even the old rules do not allow anybody to fly more than 12 hours. You cannot be in duty more than 12 hours. Wherever you are, as soon as you land, the plane stops. You've got to have a fresh, you have to replace the crew member. It has happened to me once. So the flight terminated. But thank God it was close to Houston. It was at Ellington Field. So I continued my trip by car to the final destination after a 6-hour flight from Nashville. So here you have a census. Now, if that was a random sample, how would I have treated it? Let's say that this was a random sample. How would I have
Well,
treated
what's
it?
the question you're asking? Because, I mean, the question that you've asked so far does not line up with the data that you're measuring. Right now, what you're measuring is, if this data is measuring, if you have an accident, what is the chance that it's between 1 and 3 hours, not what is the chance that you'll have an accident.
Yeah, what is the
if
chance of
you
having an
have
accident between to be in a plane with an accident between 1 and 3 hours?
But that's not
A
what
pilot
it is.
with
What it is if you have an accident, what's the chance that you are in your first 3 hours of duty, not if you.
Exactly.
So we
Yeah,
can't
but
use
is
it
the
in different
proportion if you are on a
Of course
longer
it is, but
duty?
it's not the question that we're
Is the
asking.
no? Okay, I'm changing the question. Once you're in a longer flight, is the proportion the same?
No, the proportion is different.
The proportion drops. Okay, so if I want to do that as if I want to, let's say that I had a sample, suppose that I had a sample of airline accidents, and I didn't have all the airline accidents. Suppose that I was missing data here. So
Still be measuring.
I would have 3 accidents out of 55. Only 3 occur, only 11 occur in the longer flights, over 10 hours. Duties. So what would be the proportion then? The sample, that would have been my sample proportion in that particular case. So if that would have been my sample proportion, then it would have been 11 over 55. If I want to test it with 0.27, can I test it against 0.27?
No.
Is it less likely to have an accident in a longer flight? You think probably not, but intuitively it's yes, because those are less flights. It's like asking if you are sick, are you more likely to have the common cold or HIV? Well, you're more likely to have the common cold, correct? It's more prevalent.
More common.
Same question here. So if you want to say you have 11 over 55 minus 0.27, that would be my z statistic. Can I use the z statistic here? Why? Because the sample size is big, yes. 0.27, 1 minus 0.27 will give us 0.73 divided by 55.
Well, in this case, you're not measuring on the data. In this case, no way to change it. You're taking out, so it's not going to 5 anymore.
No, suppose that we collected these data. That's what we could collect. Anyway, these data do not show worldwide data. Those are data in the US. So if you want to refer to worldwide, of course, then you have also other heterogeneities that come in the data. So this value would be equal to what? So my X was have substantial accident or not in a flight.
No, we already discussed. This is assuming we've had an accident, so we can't say as accident. We have to say the period.
Oh, no. That's actually the rate of accidents. So you're making a test for the rate of accidents here.
But in this case, what it is if has accident in flight through flight less than 10 hour, or if or greater than 10 hour.
No, I'm asking, is the rate of accidents for flights where the pilots are on duty over 10 hours
Well, yeah, but what you just wrote down.
greater than 0.25? So what is the value of this statistic?
Minus 1.17.
Minus 1.17. Okay, so that's the value of my Z statistic. What type of test do I want to do? What was my hypothesis? My hypothesis was, my alternative hypothesis, P less than P sub 0, which is the 0.27. So what type of test should I be doing? The alternative, that's the alternative. The null hypothesis was P sub 0 equals 0.27. So what is the value now of this P statistic? Okay, let's look at the value. We have 1.17. So we go to the Z-score. I will do it with the P, with actually the P-value. So what would be the P-value? Let's see where the P-value is going to be. That's the normal distribution curve here. And my statistic is negative 1.17, the value of my statistic. So I'm looking for the value of the area which is under the curve and to the left of this critical. So I'm looking at negative 0.17, 1.17, and that value is actually 0.12. So this is equal to 0.12. So if you make the type 1 error with the value of this statistic, then it's a 0.12 probability of the type 1 error. What would you do? Would you accept or would you reject the null hypothesis? Now, had I given you significance level 0.05, then your 0.05 would have been actually somewhere here, would be minus 1.645. That would have been the critical value. And the critical value in this case is less than negative 1.17. So if you were testing with significance 5%, what would be the result? Accept the null hypothesis. Okay? That would have been accept the null. Now, you cannot reject the null because if you reject the null, you have a 12% probability to make an error. That's your p-value. It's the area which is marked as black. That area is equal to 0.12, so that means that the p-value is quite high. So you don't have statistical significance. So you cannot reject the null hypothesis.
So then, what does that mean?
So that what the data suggests is that the rate, the probability of being involved in an accident, if the pilot is in the 10th or a longer hour of duty, is not smaller than that for pilots who are less than 10 hours of duty. Actually, than for pilots that are in the first to the third hour of duty. So pretty much what it suggests is long flights, short flights, things are the same. So what does that mean in terms of fatigue? If things are the same, then the fatigue has no effect. Correct?
Yes, but your data is bogus, but
if you do that, if you use this line of thought. Now, if you use this other variable here, accident proportion relative to exposure proportion, the numbers look very different though.
The upper variable, by the way.
Okay? Now, of course, here what I did is that I cheated a little bit in this, the way I did the study. And you cannot do a proportion estimation for this study. Okay? It's not really meaningful. What you have to do is whether two random variables are related or not. That's what you have to do. Whether two random variables are related or not. And what you want to do is accident proportion and hours of duty. And to be able to see that properly, you do this normalization, which is represented in the last column. And it's only then that things actually, as you see, as the hour of duty grow, the right column grows as well. Okay, so it's very important to be able to conduct the proper test and actually to choose the proper data to measure. Come from proportion estimation. Those are quite easy problems to solve, so let's see a few. Let me give you a few examples. First of all, I want to make a couple of remarks. Depending on the on the side we have the test. On the side we should have on the type of the test that we do. If we want a right tail test, always the critical region should be on the right tail, to the right of the zero of the distribution of the PDF of the distribution we use of the test of the distribution of the test statistics. So since we use in proportion z, this curve is the curve of the standard normal, and therefore the critical region should be on the right for a right tail test. Now for a left tail test, that should be on the left. Not very nice. Quite okay. Well, so the critical should be here for a left tail test. And for a two-tail test, the critical region should be on both sides. Now, if the significance level is alpha, this area is equal to alpha here. Again, this area, all the critical region is equal to alpha. But as you know, in the case of two-tail tests, the critical regions are two, one on the left, one on the right, and each one of them is equal to alpha over 2. So the total area is equal to alpha. Now with the p-values, we define what the p-value is on the right tail test. We just did it. We did it here, and that's the definition for the p-value. You take the value of the statistic that you have calculated after you plug in p hat or whatever is the measurement of the mean, and then you use this to calculate that using the assumption that p sub 0 that h sub 0 is true. So that means I want to find, since I take h sub 0 to be true, I will be using the curve of the standard normal distribution, because z has the standard normal distribution when h sub 0 is true. So that means the statistic a standard normal. If it is a statistic t, then it has, again, the assumption has so many degrees of freedom. So when I ask to find the probability that this happens, then actually this is equal to phi, is equal to 1 minus phi, where phi is the CDF, the cumulative distribution function of the standard normal distribution for z of p hat. So that would be the right p-value. Similarly, we define the left p-value if we need to do a left tail test. So for left tail test, black area equals p-value. But if we have a two-tail test, things change slightly in the following way. The value z of p, the value of our statistic, can fall either to the right or to the left. Say that it falls to the right. You put it here, but you also mark automatically the symmetric one on the other side. And now you mark correspondingly two areas, which one is on the left of this value and the other is on the right of this value. And the p-value is the sum of the two areas. So this is the trick with the p-value. Now with this, having said all of this, I want to go back to our estimation, to some problems. Those were the problems that we used for estimation of confidence intervals, but actually we can use them also. I can use them to manufacture problems for interval for hypothesis testing. So let's take one of these problems. So let's look at this first problem, which says exhibit 10.9. It's here. And the problem says the test proportion, which it implies p hat, for an interval of actually this requires a little bit of a confidence interval, actually sample size. So let's look at number 8. Do you believe in love at first sight? So suppose that college students, are asked this question. We test the actual question whether with 95% confidence we can assume that, or we can conclude that more than 40% of the students believe in love at first sight. So we have a sample of 168 students, and which is fairly big, so we have n greater than 30 because that's 168. Now x, our random variable, is the Bernoulli random variable, which is 1 if student believes in love at first sight, and 0 if not. And we want to test, the question is, do more than 30%, do more than 40% of the students believe in love at first sight? So the alternative hypothesis we have is p greater than 0.4. So our p sub 0 is actually equal to 0.4. And therefore we formulate the null hypothesis, p equals to 0.4. And that's actually the value we take for p sub 0. So we need a right tail test for proportions. Since I have p sub 0 equal to 0.4, I need to check also the property that n times p sub 0 and n times 1 minus p sub 0 is greater than or equal than 10. So now I take 0.4 times 168. Of course, that's roughly, that's over 70, definitely, and therefore it's greater than 10. And 0.6, which is 1 minus 0.4 times 168, is also greater than 10. So all the assumptions about the sample size are fulfilled. So we can use the z statistic to test. And let's take what is p hat minus our p sub 0, which is 0.4. And here we put 0.4 times 0.6 divided by the square root of 168. We will need the calculator too. So let's pull the calculator on somewhere so we can have it. Let's see what the problem says. What is p hat? The sample proportion according to the problem. Okay, and now suppose that the problem is not telling you that. I'm just modifying the problem. The problem is giving you that 62% of the sample answered yes, I do believe. So p hat is 0.62. 62% of the 168 replied that they believe in love at first sight. Well, no wonders. Young people do believe in that. So now we calculate the value of the So we'll put 0.0378. So we have 0.22, that's about 5.82, so it's a huge number. If I want to have a significance, which is, let's say, 0.05, then for 0.05, my critical value would be 1.96, actually 1.645. That is Z of 0.95. And what is Z of 0.95? We mentioned it before. It's the point that gives this equal to 0.95, where phi is the standard normal, the CDF of the standard normal distribution. So clearly the value of my Z statistic, so this is my value, this is the value of Z, what I call P hat, which is actually 0.62 here in this particular case. It's greater than the critical value, and that implies that we reject the null hypothesis. So the conclusion would be, it appears from the data or the data support that more than 40% of the students believe that in love at first sight. And that happens with confidence 95%. Now, on the other hand, if I want to see what is my Z statistic, what is the p-value? The p-value is actually 1 minus phi of the Z of 0.62, which actually, as we calculated, is 1 minus phi times 5.82. And if we try to find what this number is, tables will give you points up to 3.5, and this is 5.82, and so this is practically equal to 1, so this is practically equal to 0. So you can say that the p-value is less than 0.0001. So that means great certainty, a greater degree than certainty than, say, 95. The data are overwhelming. So, as you see, in this example, in this particular example, which we test for hypothesis, nothing has changed. All we do is what we're doing before. There are no variations. We start with the formulation of the alternative hypothesis, then we formulate the null hypothesis, then we decide what is the test statistic that we want to do. We find what type of test we want, left tail, right tail, two tail. Then we check whether we have the assumptions in place that allow us to do the hypothesis testing. Namely, what is n and what is the proportion. And finally, we do the math, we do the calculation of the value of our statistic, we compare it with the critical value, and depending on the result, we finally reject or accept the null hypothesis, and we formulate the proper assumption, the proper conclusion. If I wanted to formulate the conclusion here with the p-value, I would say the data support that students, that more than 40% of the students, of college students, believe in love at first sight. And now you put your p-value here in parentheses less than 0.0001. If you don't, if you find a value that is off charts like this one, phi of 0.82, it's practically equal to 1, then just report something like this and you're fine. So let me now go back and do another problem. I don't like this. Let's say this one. A Washington Post poll shows that concerns about housing payments have spiked despite some improvement in the overall economy. In all, 53% of 900 American adults surveyed said that they are very concerned or somewhat concerned about having the money to make their monthly mortgage payment. That problem was for hypothesis, for estimation of the parameter of the proportion. So now what I will do is that ask the following question. Do more than 53%, do more than 52% of 900 of all Americans believe, or that, let me phrase the question properly. Let's do it in a different way. Do less than 52% of all Americans believe, of all Americans are very concerned or somewhat concerned about having the money to make their monthly mortgage payment. So here again, I'm making a hypothesis for the proportion. And the question is, do less than 52%. What does that mean? That means that the alternative hypothesis is P less than 0.52, which is P sub 0. So the null hypothesis here, we're testing for proportions, again is P sub P equals to 0.52. So we have a left tail test. And of course our X is the Bernoulli random variable, which takes the value 1 if an American is concerned about or somewhat concerned about having the money to make their monthly mortgage payments or no, and this is the P sub 0. P is the probability of success that we're making the test for. Now we had 900 adults, so we believe we have a random sample. We're not told anything about the sampling, so we take for granted, we consider the sample random. So we have a very big sample, 900, it's greater than 30. So we're okay. And also P is close to 0.5, so n times P sub 0, and of course n times 1 minus P sub 0 are both greater than or equal than 10. So I can proceed with my Z statistic, to evaluate my Z statistic. Now the problem, as we stated, or we saw it, states that 53% of 900 American adults. So 53% is the sample proportion. So P hat here, the is 53 is 0.53. So we have 0.53 minus 0.52 divided by 0.52 times 1 minus 0.48 divided by 900. So this is 0.01 of, that's divided by 30, and this here is basically the square root of that's point, let's put 0.25, this simplify matters, so that's 0.5, so that gives us so we have 60 times 0.01, and of course that gives us 0.6. Now, what is the value of our, we didn't mention our confidence. Let's take confidence equal to 95%. So let's take confidence to the significant level to be 0.05. We want a left tail test. So what is the critical value now for the left tail test? That is the Z of 0.05. That's the critical value for the left tail test. We need to cut from the left area which is equal to alpha. So that value now is equal to negative 0.165, 645. And as we see, our value of the statistic is 0.06. So we accept the null hypothesis. So how do we phrase now the final result? The data support the conclusion, support with a 95% confidence that no more, actually no less than 52% of Americans are concerned with their ability to have money next month, to make their mortgage payments next month. Are concerned, very or somewhat concerned actually. To having money to make their mortgage payments, blah, 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 blah. Okay, so that's it, I guess. And with this, we conclude our today's broadcast.